So we are leaving our first unit, one of our larger ones, Unit 2, and we're entering some of our smaller units comparing more specific questions about studying data. Um, so for Units 3 and 4, they have the same idea in that we are examining relationships. And you can see there it says quantitative data, right? Quantitative means numbers. So we are examining relationships specifically among two different variables collected for the same individual that are both quantitative. So if I ask you a question about your height and your weight, are those numbers related? That is the type of thing we're going to study here. You might say, yes, I think they're kind of related. If I ask you about your height and your income, you'd probably say, I don't really think those are related, but that is the type of question we're going to learn how to study. So that is quite a bit different than what we had done before, because anytime we studied the variables for the individuals was just one data point at a time. And so it's going to be a little different now. Okay, so we have two modules in this unit. These are both quite a bit shorter. They're shorter here in our notes. They're shorter on Canvas. They are one of our core topics, though. Right, so Unit 3 is one of the mastery quizzes required for a passing grade, 2, 3, and 8. But it's kind of independent. And specifically, if you're curious, where do we use any of these things? This is some of the most common math done, slightly more advanced stats done within like a business type relationship. When I spend money on sales, how much do I expect to see as a return on that investment in sales? Or on advertising, how much do I expect to see that as an investment in sales? Something like that. So these are very common in a business relationship. There's small topics within accounting and business classes that redo almost this exact topic. It's not that we can't use it outside of there, but it is also very common within that area. Okay, so module 8 and 9, you can see 8 establishes the big topic we're going to try and learn called correlation, but also some quick things about how we study, how we plot and graph this data. So how do we study that graphically? Right, so moving on, this is page 71 in your notes. Right, so now since we have two variables for each individual and all the individuals we're studying, so the way you should imagine that now is now you have 3 total columns at least of data. You have a variable, you have the individuals, maybe someone's name, someone's ID numbers, something like that. And then for each individual, you collected 2 specific pieces of data. Each of those needs to be numbers. And so we are going to phrase one of those variables as the explanatory and response variable. We'll see what that means. Scatter plots is how we graph these. And there are 3 terms that we use to describe the scatter plots. So there are 3 categories of vocabulary terms to say how those variables are related, especially when you're using a graph. Okay, so there is a data set. I believe I didn't go through the question here in the videos, but it is in the notes. I think we've seen it before about backpack weights, and so this is a similar data set. So we have backpack weights, and so here you can see that idea of 3 columns that I was talking about. One, you just need to identify the individuals, and that's just so that you could know which one you're talking about. So Angie has a body weight of 45 pounds and a pack weight of 4 pounds. Backpack is, I think, the point there. And so you can see there's a little snippet. There's much more than 10 pieces here, but now for each value in the scatter plot, each data point, each point in the scatter plot. So this is now like a normal XY graph from an algebra type class. Normally you would have done them like this, and labeled them and whatnot. So this is that same graph. It might look a little different because the axes are a little different sometimes, but that is where this graph lives now. And so we're looking for trends. So, do students who tend to carry more weight in their backpacks, do students who weigh more tend to carry more weight in their backpacks? So weigh more is over here. Does that have a tendency to increase their backpack weight? And you can see yes. Up here there are this rough group of people who have a higher body weight and slightly more weight in their backpacks than this group. And I'm just kind of highlighting some of the main groups. So yes, there is this overall pattern of increasing, and it's not a perfect pattern, and we'll learn how to describe that. And so we categorize each of those two variables as kind of one that explains the other. And this is common. It doesn't actually, it's not always required, but it gives you a really good sense of which variable is which. So response variable is actually the secondary outcome variable. So you can see there, it says this is the variable that measures the outcome of a study. So it's kind of the thing that happens second, if you imagine collecting things over time. And almost always it should go on the vertical axis, so that means the y-axis of your scatter plot. If you were measuring like how much time and then how much weight you've lost, if people were on some diet or workout plan, the time would be the variable that happens kind of first, how long they've been on it, and then you're measuring the outcome of the study, how much weight they've lost or gained or whatever it is you're measuring. So the explanatory variable is actually kind of the one that comes first, and so it may explain. So explain for explanatory. That's why that word is chosen there. But it only may explain. We're not making a concrete statement that for sure we know this is the reason. And the whole big idea, which actually is Module 9, is we actually want to be able to predict the response variable. So if you tell me I've been on that workout plan for 2 months, I'd say, okay, hopefully you've done this then, whatever your goal of that workout plan might be. And so from a more mathematical sense, you might have heard this before, this is known as the independent variable. So in like math and like function terms, if any of that is similar, this is the x, and the dependent variable is the y. So that may or may not resonate better. I will refer to them as explanatory and response. You can definitely refer to them as independent and dependent if you need to. Okay, so a quick question: which of these here is which variable, and specifically which variable goes on the horizontal axis is the question, which means it's asking which is the explanatory. That is essentially what it's asking. So for a group of students, a teacher compares homework grades to exam grades. And so we want to know which one best explains the other. Possibly, very frequently, that means which one happens first. That may or may not be the idea, and some of these might not have time, so that might not work always. But which of them explains the other? We want to be careful not to use the C word here, and that C word is cause. We have a big issue with the cause and effect aspect here, which we will get into. It's actually the title of a whole activity later. But you can kind of think cause, but be careful, we are not directly saying it causes it. That's why we have this very light wording of may explain or contribute. It's not using the word cause on purpose. We want to highlight that later. All right, so is it homework grades that usually explains your exam grades, or is it the exam grades that usually explains your homework grades? Also, which one comes first? So homework usually comes first, and so this would be the explanatory variable. If you were to graph data points, you should graph homework grades on the x-axis. that is how we've agreed, kind of everyone agrees to interpret that. Right, at a bar, someone is measuring blood alcohol content and the number of alcoholic drinks consumed. So, right, there's probably a relationship there, but that's not really what we're right now. Is just even how do I graph it? So, does blood alcohol content explain or contribute to the number of drinks consumed, or does the number of drinks consumed explain or contribute possibly to the blood alcohol content? And so the better scenario there is that the number of drinks is the explanatory variable, and that explains your blood alcohol content. Right, so there are three big words we use, three big, not individually, we don't actually explain the word too much, three big types of categories to explain the association for scatter plots, which means for this type of data. Like the big three before categories was our shape, center, spread. So if you look at a distribution of a single variable, you're going to want to describe the shape, the center, and the spread. And then we had specific vocab and methods and calculations to do that. Sometimes we just look at it, sometimes we calculate something, sometimes we do a little bit of both. So same thing here, we have three general categories, and then within those categories we have answers to describe that. All right, so our first one is to describe the idea of the direction. And so officially, those are positive and negative directions, or neither, or no direction. But you can say in general upward or downward. That's fine also. And so we kind of always imagine moving in the positive x-axis first and asking what is the trend of the data in the y-axis. The x-axis is the explanatory variable, and so we are going to move with larger numbers in the explanatory variable and ask what's happening in the y direction. You'll see why in a little bit, why we always specifically do that. And this will be the one thing that relates back to an algebra concept in this whole entire class. Right? You have some fractions and some decimals and some kind of basic numbers to work with in this class. We do have one small topic from algebra that we use there. So generally, right, this data has a pattern of kind of going like this. We're always kind of moving that arrow towards the right. And so you can see that that arrow is heading downwards if I imagine animating it from left to right. But as I move from left to right on the x-axis, in general, my data goes downwards. So this is a negative association. All right, scatter plot 2 is hard. Let's do 3 instead. So scatter plot 3 is a little more clear. As I move from left to right, what happens in my data? I can see there's a general kind of upward trend. Right, so the more amount of time you spend on Canvas doing your homework, normally the larger, the higher your homework percentage is, the higher your exam scores are. The higher your homework percentage, the higher your checkpoint percentage might be, some sort of trend like that. Okay, so this one is the positive pattern. All right, the middle may be one of these two, maybe neither. As you're doing any of these notes ones, think carefully about it. So what's the direction here? It almost looks like there's this slightly upward trend. So if you said positive, I would say that's possible. But if we were to calculate this, I'm not sure, we have a way to calculate this later. If we were to calculate this, I'm not sure it would show us that same answer, because this is very close to just being no pattern, right? So this person here with the largest x, upward is the possible one, I think you might guess if you kind of squint a lot. But I think when you look carefully, this one here with the largest, we don't have a lot of data points either, has not a super large value, especially there's this one here with a larger y value, but one of the smallest x values. So in general, the pattern is pretty close to almost just flat. And so a flat pattern is a neither. and it just means that the kind of points are equally spread out. So if you said a positive trend, it's not as clear as a positive trend is 3. As long as you understand that, that'd be good. But if you also said, I think I would answer here, it's close to neither. There really isn't much of a pattern here. Right? As I move up, I also get one of the lowest points right away. And yeah, but if I take 1 or 2 of these out, which I can't necessarily do, I can't just delete data, then there's a lot more of a pattern. And that's because I have so few data points that 1 or 2 is very influential. So I'm going to say this is neither. Later on, right away, the next activity, we'll have a way to calculate this and help us out, because it can be a little hard just doing this visually. Right. The direction will be something that the calculations... Oh, there's another interesting question there. So going back to drinking. So if a group of people at a bar, do you think the relationship between blood alcohol content and number of alcoholic drinks will be positive, negative, or neither? Just a reminder, number of alcoholic drinks should come first. So kind of which of these graphs should it be? Alcoholic drinks would be at the x-axis, and blood alcohol content would be on the y-axis. Right. The more you drink in general, the higher your blood alcohol content. And that is a positive relationship. So larger on the x-axis should in this pattern should be associated with larger values on the y-axis, which are blood alcohol content numbers. Right, and that'll be a little different for everybody. It doesn't mean it has to be a perfect relationship. You have people's like body, I don't know, chemistry, and just like male versus female and height and weight that might all affect that. And then you just have time. If you ask people how long, you might have drank it over 2 hours versus an hour versus 5 hours. But averaged in general, more drinks will mean a higher blood alcohol content. Right, our second big term is strength, and that is how strong that pattern is. The opposite of strong would be how weak that pattern is. And so here we have a positive pattern. Here we have another positive pattern. And in the middle we don't have much of a pattern at all. Maybe a bit of a negative pattern. Maybe, a little hard to tell. All right, so let's look at 1 and 3 since they're very clearly positive. Which one has a stronger pattern? So essentially, which one is clustered closer to this imaginary line that I'm kind of drawing through them? And it turns out that's not going to be imaginary. We're going to calculate that line, and it's specifically going to be a line for our class. So this one here is the strongest. The pattern kind of has the closest, the tightest part of the pattern there. Scatterplot 3 has a very clear pattern, but it's not as strong as 1. So this is next strongest. I can just say strong, strongest. And Scatterplot 2 barely has a pattern. I don't really see much there at all, so this is definitely the weakest. And it's also just a very weak pattern in general. It almost looks like no pattern. And so in terms of the strength, 2 is definitely the weakest. Very, very weak in general. 3 is still a very clear pattern. Again, we will have more formal ways to calculate these. And 1 is almost a perfect pattern. All right, lastly, we have the idea of form. This is like related to shape. So shape of the pattern, in a sense. And it just turns out that it's you're taking your first stats class, probably, and this is the introduction, and so we can only cover so much material in each of the topics we're choosing to cover. We are going to focus on calculating these associations of quantitative data when we only are looking at a linear pattern. And so that the pattern looks like it fits a line, roughly. So if our data is not a linear pattern, that's nothing wrong with it. It also doesn't mean that it could have a really strong linear pattern, but that just means we won't be able to study it. That is a very common type of thing to study in this field. And you could easily study it in a class that has this as a prerequisite. So for example, as a business major, I had an intro stats class and then like an additional business stats class. I was a business major before I was a math major. Um, and in that class, we talked a lot of how to study these. And within StatCrunch, it's just the next line down and how to study them. But then you just have a little bit more complex requirements and how to set them up and what to know what to do. So definitely something you can do, just something we won't do in this class. Doesn't mean it's wrong or bad, just we're focusing on lines right now. And so what are the clear lines? This pattern is a very clear linear pattern. That one almost looks like the data is completely on a line, so that's extra special. Normally we see patterns closer to this. If we do see a pattern, sorry, that's a terrible line. Something like that. Right, and these other ones here have a very clearly curved pattern. And so those are out for us. Just for us, we will not get into how to study and think about those. And so our form needs to be linear. Notice up top now, that is one of the topics in this module here, linear relationships. So scatter plots are how we plot them. Linear relationships we need to work on are the only ones we choose to work on in this class. That is always the first stats class. We study linear relationships. And so correlation is the last topic we need for Module 8. I think that is all that is left for Module 8. Okay, so it says Introduction to Linear Correlation, our second activity here in Module 8. R. Just this little general R term. So when we calculate stuff in stats, we usually like to give it a specific label. And so the symbol that's going to label a correlation is called R. So R is a number that's going to describe both the strength and the direction. So you do have the direction, the strength, and the form from earlier, but the form is like a yes-no thing. Does it look roughly linear? Then we'll study it in our class. If not, you just need to wait till later or never to learn about it. And so we're still going to focus on direction and strength. And direction and strength are both captured by this number R. And so really this number R is the highlight of this topic called correlation. And correlation relates to the English word that, correlated, things go together. So that is going to be helpful as a vocab word there. And so below there's a bunch of different scatter plots. So some things about, it's a number we calculate, the correlation. If you ever see in our words the word measure, measure is something that means we calculate it. So we had a measure of center, a measure of spread. There's like the word measures there in a slightly different context, but that almost always means that we are going to calculate something. Okay, so we're not going to only rely on pictures and kind of intuition. So some properties about the number R. So if you calculate R, it should be positive when you have a positive association or an upward pattern. It should be negative for the opposite. All right, and here's the bigger one. What about, how does it describe strength? So that's the one that's a little more subtle. So R ranges from -1 to 1. I'm going to put 0 in the middle. So we already said that when it's positive, it just means the line's going up. When it's negative, the going down. So you want to make sure you don't think negative is anything bad. All it means is that the line looks like it's going down. And so if your correlation, like when do you have a better, which would be stronger correlation, normally we're looking for stronger patterns, that would be when you're closer to the end of this range, the -1 and 1. The middle means very little pattern. So an R of 1 means it looks like a perfect line heading uphill, and an R of -1 is a perfect line heading downhill. So perfect on 1, perfect on -1, and 0 would be no pattern at all. 0 for us would represent the there'd be no correlation. Okay, so there's a bunch of different correlations at the bottom. I'm going to even avoid looking at them and label at least one of these graphs here. This first one here really, sorry, the second one really looks like they're on a perfect line. And if you see in our, so this is a matching problem, we do have we do have one out of all these correlations, one of them has +1 as its correlation. And that must be this one here. Perfect line, positive, increasing. Okay, our matching pattern also gives us 2 negative ones. So there should be, out of all these scatter plots, there should be 2 of them that have a perfect negative pattern. And so that's 7 and 9. And again, the closer to 1 or -1, the stronger the pattern. Right, so let's just go through and pick. We should have a -0.44 in here somewhere. And so that should be a negative pattern that is kind of strong. You know, somewhere right in the middle between 0 and 1. So it shouldn't look perfect, but it shouldn't look like no pattern. So I think that is here at 6. -0.44. It's very clearly negative. Out of our multiple matching scenario, this is the only one that can be negative also. Right, let's kind of work our way inwards. So 0.94, so almost 1. So it should be a very strong positive pattern. And I think that would be this one here. 0.94. 0.88, so very similar. Those are not much different. So if we got that wrong, they are very close. So this is not something that you can easily tell. So correlation is a little hard to tell that perfectly by just a graph. That's the advantage of calculating it. You know, in reality, you'll be given the data, any real life scenario, and be able to calculate it, or you'll know which one's which. So it should be something that looks pretty similar to scatterplot 1, a positive pattern, but maybe just not quite as well correlated. And you might say maybe that is 8, right? 8 has a really good pattern except for the outer point. Maybe say 8. If you said 3, I think that'd be a good answer also. So either of those, these are not easy to tell. So I'm going to say, I think my guess is 0.88 for scatterplot 8. And then 0.75, I was thinking 3 was just a little less correlated than 8, so that's where I'm going to put 0.75. That was another option. It's similar, positive, pretty strong correlation, but not quite as good as the first two. That could be 3. Right, lastly, we should have one that is somewhat positive, kind of halfway, 0.55. And this one is a little hard to tell. So I think that's probably going to be scatterplot 4. Scatterplot 4 and 5, the visuals. So one thing about this exercise too, it highlights, it's a little hard to do this perfectly visually. Because when you match these up, if you had done it a different way, you might have got slightly different answers. And that's okay. We won't ask you to be perfect at this, just to be able to really roughly estimate them, especially positive versus negative, and in general, is it kind of strong or kind of weak. So that one might have somewhat of a positive pattern, and then maybe 5 doesn't have much of a pattern at all. Because if 5 does have a pattern, it looks like it might be negative. And so maybe that last one left is 0.01. Maybe 4 is 0.01, but 5 doesn't really look positive, so how these all match up, not sure if that makes sense. So sometimes it's a little hard to estimate these, but we definitely got a good idea in roughly what they look like. You do not have to be an expert in matching these up visually. Okay, and lastly, this is more something to read through. I'm going to very lightly talk about it. This is a huge phrase in stats in general. Correlation is not causation, or correlation does not imply causation. Some other ways to say that. So mathematically, just because two variables are correlated, or the idea of associated, does not mean that one of them causes the other. And part of it, we wouldn't even know which one causes which. If I switch which one is my x and y variable, I still get the exact same correlation between them. My scatter plot might look different. It would still be a positive or still a negative pattern, but it's going to have exactly the same correlation. So first off, it doesn't even tell us which one is the proper cause and effect, which one is the proper explanatory and response variable. We might be able to make a good idea of that. So, but in addition to that, there are lots of reasons why one variable might be related to another that has nothing to do with one of them causing the other. Okay, so if you want to read through this here, well, I'll try and read it pretty quickly. So a more elementary, widespread confusion is that between correlation and causation. Our topic right now. Studies have shown repeatedly, for example, that children with longer arms reason better than those with shorter arms, but there is no causal connection here. Just to pause, that is true. If you conduct a study to figure that out, you'll see that's true. Children with longer arms reason better because they're older, right? Why would someone who have longer arms reason better, essentially smarter, than someone with shorter arms? Most of the time, that person with longer arms is older. It has nothing to do with specifically just being taller. You're just usually taller if you're older, especially in children. Okay, so that is an issue in how we need to think about this. All right, another one. Consider a headline that invites us to infer a causal connection, in all caps, bottled water linked to healthier babies. So if you use bottled water whenever you're, feeding and giving water to babies, somehow they're going to be healthier. And that sounds a little closer now. Right? Without further evidence, though, this invitation should be refused, since affluent parents, affluent means wealthy or rich, since affluent parents are more likely both to drink bottled water and to have healthy children. They have the stability and wherewithal to offer good food, clothing, shelter, and amenities. So it's not that it's the water causing the healthier babies, but these babies are healthier in general because they are more likely to be in a wealthier family. And then the next one gives it the similar example that shows how silly this could be. Families that own cappuccino makers are more likely to have healthy babies for the same reason. Making a practice of questioning correlations when reading about links between this practice and that condition is good statistical hygiene. Statistical hygiene is a phrase that made up by this person here, but you don't need to know that long term. But so there's lots of reasons that background variables, which are going to be called lurking variables, might actually be an explanation for why that pattern exists. First go-to for a lurking variable, always ask about the idea of money and some sort of kind of affluent. You can see that pretty quickly came up there. So that could show up in something like organic food. Does organic food make you healthier? Maybe it does, maybe it doesn't. We can look up those studies, but that just might be associated with buying healthier food to start, and it might not be organic. I'm not making a claim either way. You might want to look that up. Just to clarify some of these phrases here. So there is no causal connection, right? So does one variable properly explain the other and cause it? That is not something that we can determine with just our methods right now of calculating correlation and looking at a scatter plot. So that's the idea. One will not necessarily be the cause of the other. The explanatory variable might explain it mathematically, and we would call it the explanatory variable for a reason, but that might not be only the reason or very specifically the reason. How do we prove that? We're going to talk about experiments later, and a properly set up experiment can help us determine that. Just really quick, in the children with long arms, reason better than those with short, what is the explanatory and response variable? We are frequently going to think about the idea of explanatory and response variable. Let's go ahead and write those down right now then. So what is the thing you're kind of imagining measuring first, and then the thing you're testing to check that? So the explanatory variable is arm length, measured in, some inches or feet or something. What is the response? Reasoning skills, right? It said something about reasoning. If you called it intelligence, that's the rough idea and what they're talking about. We don't know exactly what they meant. Maybe they give them some puzzle or some test or something. And mathematically, these variables are strongly related. Naturally, we might think one of them causes the other. We're going to put explanatory as the arm length from the phrasing of the context. But in reality, these are both better explained by a background variable called lurking variables of money, or we'll say wealth. In general, wait, no, that was, sorry, wealth was the, wealth was the water bottles. Those capital letters, keep on looking at them, confusing me. So lurking variable is the age. If your arms are longer, in general, if you find someone whose arms are longer than someone else and you know nothing about them, you can still take a good guess that that person might be older. And someone who's older will have better reasoning skills than someone who's younger. Within kids especially. That doesn't mean when you're 30 versus 25 you might reason any better, but when you're 10 versus 5, you'll probably reason better. Okay, one other really quick example. So the x-axis here is internet users per 1,000 people for countries. So these are 20 different countries. So it's essentially a measurement of how many people have access to the internet and then life expectancy. So you can see that if this goes all the way down to 0, almost 0, looks very close. So some countries, this was in 2009, nobody has access to the internet. And then they're all their life expectancies. This correlation is a 0.72, which is quite strong. And so, does that, how does this scenario make sense here? So you can see the sentence there. Someone who, let me go back maybe, larger numbers of internet users, which means more, a larger number on the x-axis, correlate with longer life expectancy. Right, in general, you can see there's a pattern here. It's not a linear pattern. We can always calculate the correlation, even if it's not linear. On our own, we should judge if it's linear or not, so that's not great here. But we did it anyways. So someone who confuses correlation with causation might suggest that if you have a country and you want to improve its life expectancy, to get more people on the internet. So like go around and distribute little tablets that connect to the internet somehow, and people are going to live longer. Is that directly going to cause them to live longer? No, right? Maybe it actually has some very small effects. People can look up some basic medical stuff besides all the other stuff they might do on the internet. But what is providing someone access to Facebook and Instagram going to do for their health? Probably very little, right? Like what actually would improve their health? Probably they need access to health-related care, whatever that might be. So there is a pattern here, right? But what's the lurking variable here? These are probably countries that are rich versus poor. A richer country is going to have more people have access to the internet and probably has a higher life expectancy. And there's even one kind of outlier in the group. Very low internet usage, but very high life expectancy. So there's even kind of some outliers within here. All right, I believe that is the end of Module 8. And so I will stop this video and start Module 9. That's our second and final module for Unit 3.